Hi and welcome. In today's video I'll explain what's the confusion matrix. I will explain to you what's the confusion matrix for two classes and also for multiple classes. My name is Felipe, this is the Data Science Bits channel. Please subscribe and click on the bell button to receive notifications with every video that I post, and also follow me on LinkedIn. As in other videos, let's go to the website of the channel. So the address is this one. I'm providing it also in the description of the video. If you scroll down, you'll see this section here. These are the elements of the confusion matrix from balanced distributions. So what do we have here? So on the y-axis we have the frequency, how many times something occurs. And on the x-axis we have the output probability. So here we have a machine learning model that has been trained on labels, and the labels are zeros and ones, or what we call the negative classes and the positive classes. And the output probability is the probability that the model is providing that specific case is in the positive class. So when you say probability 100%, the model is 100% certain that this pertains to the positive class. When you have probability equals 0, the model has certainty that that occurrence, that example, is in the negative class or is not in the positive class. And in practice we have distributions. One distribution near 0, one distribution near 1. This distribution near 0 is the distribution of the actual negatives. And this other distribution on the right is the distribution of the actual positives. So you see that this is closer to 0, the peak is closer to 0, and this other peak is closer to 1. In reality, we will always have distributions that crosses, that have intersection, because the model is not perfect. So there is some confusion, let's say, between the two classes. And to really define the classes, you need to establish a threshold for the positive class. This is the dotted line here on the vertical. Okay? So this is one example of a place where we could position the threshold. It means that everything above the dotted line is positive for the model, and everything below the dotted line is negative for the model. So we have 4 possibilities, and these are all the ones that are here on the legend. True negatives, false positives, false negatives, and true positives. So these are actual negatives. And because this red portion of the curve is below the thresholds, they are actual negatives being predicted as negatives. So they are true negatives. It's denoted by Tn. When you go above the threshold on this portion of the histogram, you have actual positives being predicted as positives. So these are true positives, Tp. Now we have the tails of the distributions. So first, this tail here in green. This tail, we know they are negatives, they are actual negatives, but they are being predicted as positives because they are above the threshold. So these are false positives, Fp. This other portion here in orange, we know they are positives, they are actual positives, but they are being predicted as negatives because they are below the threshold. So these are false negatives, Fn. And the threshold can be positioned in many different places, from 0 probability to 1. And you can vary the position of this threshold in small steps, and you can see how these 4 quantities change. I still haven't told you what's the confusion matrix. These 4 quantities, you can organize them in a matrix. As I'm showing here, you could place the actuals in the vertical and the predicted in the horizontal. And when you have, for example, 0 as actual and 0 as predicted, these are the true negatives. And what you do is that you write on this square here in the matrix the amount of true negatives. And on the other block here in the diagonal, you could have actual positives, ones, and predicted positives. These are the true positives, and you write the number of true positives here in this square. And outside of the diagonal, that's in orange, you have the false negatives and false positives. These are the errors of your model. And you also write the numbers, the quantities of false negatives here and false positives here. This is the confusion matrix. If you sum up the 4 squares, you will have the total number of examples that you are using to provide the confusion matrix, for example, in the test set. Or you can normalize the confusion matrix, and there are basically 3 ways of normalizing it. You can normalize it row-wise in this direction, you can normalize it column-wise in this direction, or you can normalize it overall, so dividing all the squares by the total number of examples. What we have discussed here is for 2 classes, so we have a machine learning model that's a classification model that has 2 classes as labels. What happens when we have more than 2 classes? I will provide an example from scikit-learn that's using the Iris Dataset that has 3 classes. The 3 classes are setosa, verscolor, and virginica. So you have the true labels or the actuals on the vertical, the predicted labels on the horizontal, and like we were discussing, you have raw numbers for each square. So here you have actual setosas being predicted as setosas. They amount to 13. You have 10 verscolor versus verscolor, you have 9 virginica versus virginica. But the model is not perfect, you have some examples outside of the diagonal. Now the normalized one, but this is normalized row-wise. 1, 0, 0, so this amounts to 100%, 0, 62%, and 38%, this amounts to 100% in this row, and this amounts to 100% in this other row. If your positive class, the important class for you in the model, is virginica, let's say, these are the true positives, right? This block here are the true negatives. And everything outside these 2 blocks are the errors, the false positives and the false negatives. So it's exactly the same logic. It's just that when you have multiple classes, you must tell what is the positive and what are the classes that are within the negative. So by doing that, you can reduce a multi-dimensional confusion matrix to a 2-dimensional confusion matrix. An important lesson in this video is that although we are always using confusion matrix everywhere when we're doing data science, we need to remember where it comes from. It comes from the distributions. So we always have to go back to the fundamentals of statistics to really understand what we are doing. Okay, so that's all for today. I hope this was valuable for you. Let's always remember to go back to the basics. Don't forget to subscribe and see you in the next video.